Okay, my third and final Lewis Structures lab. When I was a kid, these guys were a cartoon on MTV, Beavis and Butthead. I think this is Beavis and this is Butthead. And they used to run around and cause all sorts of trouble and would shout, breaking the law, breaking the law, breaking the law. And that's what we're going to talk about today, right? Breaking the Lewis structure laws. If you want to pause and Google some Beavis and Butthead clips, it might be a good use of your time, or maybe not, I don't know. At any rate, it will turn out that there are a multitude of exceptions to the octet rule. Here are some of them. The first are called expanded octets. So atoms in the third period and beyond can have more than 8 electrons in their valence shell. Here's an example. SF6. Sulfur is here. So it has 1, 2, 3, 4, 5, 6. Fluorine is here. 1, 2, 3, 4, 5, 6, 7. 6 times 7, 42 plus 6. It has 48 valence electrons. I got to distribute 48 valence electrons around this molecule. And so if you were drawing it, you might predict something like this. I hate it when my marker does that. Whoops. This just came out really poorly. Ignore this for a second. F, 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 F. Sulfur in the middle, fluorines around it, and then I'm going to start littering this with electrons. So there's a bond. You guess it looks something like that. Again, 2, 4, 6, 8 electrons around each fluorine atom. So 8, 16, 24, 32, 40, 48 electrons. Right? It works. With the notable exception that sulfur has 2, 4, 6, 8, 10, 12 electrons in its valence shell. Is that okay? Well, remember that sulfur is here, right? So atoms which are in the third period or bigger can violate the octet rule. They can have expanded octets. And so why does any of this happen? Well, it will turn out that in n equals 3, there are low-lying d orbitals, right? And these can house extra electrons. If I'm in the second period, right, notably carbon, nitrogen, and oxygen, you can't do that. All right, there are other examples as well. So incomplete octets. Some atoms, notably boron and beryllium, can have less than 8 electrons in their valence shell. BH3. Right? It looks like this. So it has, boron has 6 electrons in its valence shell. It has an incomplete octet. There are also odd electron species. So the famous example here is nitrous oxide, laughing gas. It has 5 plus 6, 11 valence electrons. And if you draw the Lewis structure, I gotta see if I can get this right. I think it looks like this. 2, 4, 2, 4, 6, 8, 10, 11. Right. Nitrogen in this one has 2, 4, 6, 7 electrons. Odd electron species will always violate the octet rule. And notably, these examples are fairly uncommon. I told you if they got an odd number that you probably did something wrong. They have a specific name. They're called radicals. They're highly reactive. And the fact that not many of these things exist, or when they do, they're very unstable, is actually taken as proof for the Lewis model, or support for the Lewis model. At the end of the day, deciphering the best Lewis structure often involves a lot of guess and check and deciding which rule you'd prefer to break. Is it better to violate the octet rule or to have some formal charge present? You may not know. And figuring out which one you use, right, involves a fair amount of chemical intuition. For the record, right, given these choices between the two, would you rather violate the octet rule or have formal charge present? Well, the answer is here, you want to violate the octet rule. And figuring that out is part of the normal process of working with Lewis structures. As you work through these, there's probably lots of ways that you could figure out the answers to these questions. I'm not going to detail them to you, but I would encourage you to work through it and stretch yourself a little bit and see if you can figure these molecules out, because they're actually fun at the end of the day. All right, that's it. I'm going to stop here, and I have one more set of lectures for you about VSEPR, and we'll go from there. All right.